Okay, let's get started. So any homework questions? Yes, sir. 18? Okay. All right, let's take a look. So 18, we have the integral of sine cubed theta, theta, times cosine of theta to the minus 2 d theta. Okay. So one nice thing about this problem, this is a sine raised to a power, cosine raised to a power problem, and one of them has an odd power. And when one has an odd power, typically that's good news for us. And so what we do when the sine has this odd power, we could throw this cosine down on the bottom if we really wanted to, but we don't have to. So let me show you what I mean. So what I want to do is let's rewrite. So what I want to do is I want to just pull one of those sine thetas out to the side and then write the times the other two, sine squared theta. And then we've got this times cosine of theta to the minus 2 d theta. And then I want to change all the other signs, other than the one I pulled off to the side, turn those into cosines, if possible. So sine of theta, so sine squared theta plus cosine squared theta equals 1, right? So sine squared of theta is 1 minus cosine squared of theta. So I could rewrite, and this is equal to the integral of sine of theta, and then I'm changing that sine squared theta into 1 minus cosine squared of theta times cosine to the minus 2 of theta d theta. Now that I just have this one sine sitting here and everything else is written in terms of cosine, I could, if I wanted to, make a u substitution. So let's let u be cosine of theta, and then du would be negative sine theta d theta. So to make the substitution, I need a negative in here, so let's add it in, which means I also need to add a negative outside to cancel it out. And now let's make our substitution. The negative's still there, but inside I get 1 minus u squared, 1 minus u squared, times u to the negative 2, u to the negative 2, and then negative sine theta d theta all becomes du. Now I could multiply through that u to the minus 2 if I wanted to. And I could write this as negative integral u to the negative 2. And then u to the negative 2 times negative u squared is just minus 1 du. All right, now I can just use the power rule, take an antiderivative. The negative's still there. U to the negative 2, I want to raise it up a power, so negative 1, and then divide by negative 1. So this would be negative u to the negative 1. If you want to write that as 1 over u, that's great. And then antiderivative of negative 1 is negative u plus c. Okay, I could multiply through by the negative. And also I could plug in for u. And I remember that u is cosine of theta. So this is negative times negative is positive cosine of theta to the negative 1. So if you wanted to, you could write this as 1 over cosine of theta, also known as secant of theta, right? So if you wanted to write that secant theta, that's great. Minus cosine of theta plus c. I lied. Plus. That's even better.
Yeah, I tried to do like take out a side.
Yeah, so
Minus got up.
does this make sense?
Yeah.
And it actually, what's so amazing about this method is it doesn't matter what these two are. If one of them is odd, just take one out to the side, leave the even number there, switch the even number into the other guy, and it just works, which is pretty nice. When they're both even, it's horrible, but it is what it is. Yes, sir.
Like cosine, negative second power.
Yep.
Cosine, second power, just scale.
Here,
Where's that?
you can do it. So nothing would really change. So if you multiplied this through, you could get cosine to the -2 of theta minus 1. Yes, you could do that. That would be fine. Any other questions? Yeah.
31.
31. All right. We have the integral of tangent to the 6th of x. 31, we have integral of 20 tan to the 6th of x dx. All right. Well, first thing that I can say is there is like officially a reduction formula, right, for tangent to the 6th of x. So we could use it if we want to. Okay, that said, what if we decided we didn't want to use it? Well, how would we go about something like this if we didn't have the reduction formula to kind of go through it that way? Well, first of all, 20 can come out. Second of all, well, what is all of this? We've got tangent to the 6th of x. If I let u be something like tangent of x, let's say, then the derivative would be secant squared of x, right? We don't have any secant squared of x. So officially, that's pretty tough. So how would we do it? Well, we could change some of the tangents into secants if we wanted to. Or if you really wanted to, you could turn all of the tangents into secants. So it just depends on the way that you want to go about it. This is one where I kind of feel like you might want to play with it a little bit to figure out. Okay, let's see. So this is 20 integral of, there's kind of three ways we can go with this, okay? We can either say that this is tangent squared, because, okay, if we're going to replace tangents with secants, we have to do it in squares, right? So this is tangent squared of x cubed, right? Which is also tangent squared of x times tangent squared of x squared, or we could just think of this as tangent squared of x times tan squared x times tan squared x. So we could either replace all three of them with secants, we could replace two of them with secants, or we could replace just one of them with secants, whatever feels like the best move. Now, here's what I think I would like to do. Let's just replace one of these with secants. If we do, then I get tangent squared of x let's go ahead and say it's squared, or it's to the fourth if you like. And then this one can be replaced in what is the identity? 1 plus tangent squared of x is secant squared of x. So tangent squared of x is secant squared of x minus 1, right? So this is secant squared x minus 1 dx. So far, so good? Okay. So now let's multiply it out. If I do, then I get 20 times integral of, this is tangent to the fourth of x, times secant squared of x, minus tangent to the fourth of x dx. Everybody feel good about this? All right, so here's the fun thing. If I make a u substitution for tangent of x right here, the derivative of secant squared of x, so I can do this piece. This piece I can't. But I could do the exact same thing again for this one and turn that into a tangent squared of x times secant squared of x minus 1. So now we would break this into two integrals. There's 20 times integral of tangent to the fourth of x secant squared of x dx minus integral of tangent to the fourth of x dx. This one is just a u substitution. This one, I have to do the exact same thing again. Does that make sense? And what we've actually done right here is we've used the reduction formula. Once I do a u substitution here, so I'll say, let's see, where should I write this? I'll let u be equal to tan x, and then du is equal to secant squared x dx. Then over here, this turns into 20 integral of u to the fourth du. And then this one I just need to keep working on. This is integral of tan squared x times secant squared x minus 1 dx. This is easy. So we're basically done with this one. This one, now I need to multiply through by the tangent squared x, do another u substitution. So basically it looks like we'll probably end up doing this 3 times to get it done. So this one's basically done now because this is just u to the 5th over 5. Plug back in for u and you're done. This one we're going to have to do the same process to get it down to tangent squared of x, and then we have to do it again, and then we can integrate it. So I could keep going, but does that answer your question? Yeah. This is actually the exact same thing that the reduction formula does. It just spits out, the reduction formula just spits out the antiderivative right here. And then it just leaves you with a minus tan, integral of tan x to the fourth. That's all. Other questions? Yeah.
This one was in the homework.
Okay.
But if I look at tangent, that's like to the 7th x.
Yes.
And the secant, that's to the 5th x. So if they're both on, how would you go about?
Yeah, tangent and secant are a little bit different than sine and cosine. So you said like tangent to the 5th x, secant to what?
Like the 7th.
7th x. Okay. So dx. What I would probably say is, all right, I can't turn let's see. So what I really want is to either use u as tangent or u as secant, right? So I'm kind of looking at, okay, if u was tangent, then I'd have a bunch of tangents, but I'd need a secant squared. But if I have a secant squared, that means that all the other secants, meaning 5 of them, would be left over, right? And that's not great because I can turn 4 of them into tangents, but then I'd have 1 left over, so that's not amazing. Okay, if I went with secant, the derivative of secant is secant tangent, correct? So I would have to take one of the tangents out in the u substitution, leaving 4 of which I could turn into secants, and then we're good. Does that make, okay, so basically what I'm saying is, okay, what if I said here that u is secant of x, then du is equal to secant x tangent x dx, correct? So this would be written as integral, there's a tan x that I'm just going to set aside. There's a secant of x that I'm just going to set aside. I need those for du. What is left over? Tangent to the 4th, right? This is tangent, and if you like, I could write it as tangent squared of x squared. And then I also have how many secants left over? 6 of them. So I have a secant to the 6th of x dx. I'm not substituting yet. I just know kind of what I need. So here I could rewrite this as tan x, secant x. Now I want to turn all of these into secants. But tangent squared of x is secant squared of x minus 1, quantity squared, times secant x to the 6th dx. And now it's perfect because all the secants become u's, the tan x, secant x dx becomes du, and now I could write this as u squared minus 1 squared times u to the 6th of integral du. And now that's relatively easy. Does that make sense?
Yeah. So how did you know to do the
How did I know to go with secant? Only because tangent just didn't work. Because if I took tangent as u, then the du is secant squared of x. So I need a secant squared of x set out on the side, so to speak, leaving me secant to the 5th of x. I can't turn secant to the 5th of x into tangents. And that's the problem, is I need to be able to turn, once I set aside the stuff I need for du, everything else I need to turn into whatever u is. And so I need like an even number. Yeah. Yeah. 28. Yes. Okay, so we have integral secant to the 4th. So 28, we have integral of 6 secant to the 4th of x dx. All right. So, so the first thing that I would think about is, okay, what could I potentially substitute for? And the funny thing is that secant seems like the only option, but it's no good because there's no tangent, right? Because if the derivative of secant is secant tangent, there's no tangent. So what do? Well, what if we substituted for tangent? Well, there's no tangent, but maybe it's okay. Let's see. So what if we let u be tan x? Then du would be secant squared x dx, right? So two of these secants are going to go away. And then what I think I need to do is maybe let's turn the other two secants into tangents. So I could write this as 6 integral. Two of the secants I just want to hang out to be substituted for. The other two secants I'm going to turn into tangents, and secant squared of x is 1 plus tangent squared of x. So this is 1 plus tangent squared x. But now I can make this substitution. The tangents are u, the secant squared x dx is du. So I could write this as 6 integral of 1 plus u squared, 1 plus u squared, and all of that is du. And now we're good to go. Make sense? Yeah, these are, I mean, to me, this is actually kind of fun, just to kind of think through, like, okay, the good news is options are limited to some extent. It's kind of like if you're dealing with sines and cosines, typically you're substituting for sine or you're substituting for cosine. If you're dealing with tangents and secants, usually it's either you're substituting for tangent or you're substituting for secant. So you kind of have to just think, well, which one will make it work? And you might go down the wrong path to start, but it's easy enough to kind of see, I can't substitute that way, where I can. Yeah. Anything else? Maybe let me just ask everybody a quick question. Let me see. Some people have. Somebody said 28. I think we did 28, didn't we? Yeah, we did. Good. So I was just wondering, how's it go? So this class has been, I'm teaching it maybe a little bit differently than I would normally, in the sense that the technical lecture is online, right? So you're watching the lecture online, and then we're doing this homework stuff in class. Have you been feeling like that's a good experience? Or does anybody have any comments about kind of the structure of the class so far and how it's gone for you? Yeah. Less engaging? Yeah, so the comment was that it was less engaging. Hopefully the class time is engaging, but are you kind of saying you would prefer to learn the lecture live than to learn the lecture like remotely? That would be. Yeah, I totally get it. I don't even disagree with you, really. I think that, the optimal world would be that I would just do the lectures as normal. That said, my personal feelings about it are, although I totally agree with you that that's kind of the optimal, it doesn't reverse. Like if I do the lecture live, typically what I found is students don't then spend like an extra hour watching example videos. People are like, I got this. And so they just do their homework and that's it. So what I do like about this is I feel like it's almost, this sounds horrible, but it's sort of true. It almost forces you to spend a little bit more time with the material. because it's kind of like you have to almost watch the lecture outside of class. So that's like an hour to 3 hours a week, right? And then you pretty much need to do your homework. And so there's value in coming to class. But I agree with you overall that like, it's nice to have a real live person teaching you the stuff. There's no question about that. Yeah.
I agree with that. It would be nice to have the lectures in person, but I feel like this is better, at least for the time being.
It is what it
I
is.
like it.
It is what it is. Yeah, we're making the most of things. Hopefully, I just wanted to get a feel for, is everybody like every day kind of booing when they have to watch the lecture online, or how is it going? And do you feel like you're picking it up well enough from the online lecture? Obviously, it's not how we would have written it up, but is it going all right is kind of what I'm asking. Anybody else have a comment on that? Yeah.
I feel like I get a lot more out of doing the homework because I can I do it on my own, and then if I struggle with something, then we can go into class and like check in, and then I can actually like check back for my work. It's not just like getting the homework done to get it done, actually like going through and like figuring out the process and like making sure everything's right.
That's good.
I like it.
Yeah, it does. It definitely gives more time with examples than we usually get to have. When I teach normally, I take homework questions at the beginning, but you just can't do 50 minutes of it, right? It's kind of like I'll take one, maybe two if there's time, questions at the beginning, and then we get into the lecture, and that's what we do. So I do think that there are advantages. It's not all advantage, but there are some. So. Has anybody been to the math lab?
Yeah, I went there.
Was it helpful?
So I walked in and there was like a variety of like some people helping math.
Yeah.
And it was so basically you get a student who's already done the class.
Yeah.
And kind of knows what they're doing, and then also has to look things up just like so yeah, it was good.
Yeah. Okay. So any other comments, just as a kind of, I guess we're a third the way through the semester, believe it or not, it kind of flies. But just kind of checking in, I want to make sure that everybody's feeling good about the format. I personally think that this is like 20 times better than if we would have been doing this in the gym. So it's kind of like, it's not the best of the best, but it's not in the gym. So that's kind of how I feel about it. So hopefully everybody's doing well. I want to make sure that everybody is actually enjoying their experience in this class. Cal 2's hard. I don't know if you've discovered yet, but it is a difficult class, no question about it. So I think that the more time you spend with the material, that's going to be good for you. And I do think that because of the way we're teaching it, you're spending just a little more time with the material, and that's good. So, cool. Any other comments? Okay. Well, I think I've done almost like every problem in this section almost in class between the last 2 days. So I will leave the rest for you. Leave it in your capable hands. So I guess that this section is due tonight, correct? And then the next section on trig substitutions is due Friday. And so I would like it if everybody had watched the lecture over trig substitutions by Friday. So we have some good stuff to talk about. Hopefully try to do some of the problems yourself too before then, and that will make it the most productive. Other than that, I think we're good to go for today. Have a good day, and I'll see you Friday.